Good afternoon, dear members of the jury. I'm Petro Deminev, an 11th grade student at the Nicolas Lyceum from Kiev, Ukraine. I would like to present to you my work on the topic Solutions for Optimizing a Blast Furnace. My interest in the operation of blast furnace arose because my father worked in the metallurgical industry. The blast furnace industry plays an important role in many economic strategies. The conclusions of the work are an example of solving production problems. They can be used to achieve the goals of the oil development and post-war reconstruction of the Ukrainian industry. Let's get acquainted with the principle of operation of a blast furnace. This is a large steel pipe into which raw materials are sewn, and heated air is blown into the bottom. These raw materials are discharged to the bottom of the furnace from 6 to 8 hours, where they turn into liquid slag and liquid pig iron, which are the final products. These liquid products are drained from the furnace at regular intervals. A series, a series of chemical reactions take place in the blast furnace depending on the temperature and direction of the place. This is illustrated in Figure 1. Iron in processed ores is reduced using carbon, which is supplied in the form of coke. In the blast furnace, the coke is burned with the supply of hot blast, forming carbon monoxide, which reduces the iron. It is important to maintain a high temperature, about 1700 at Celsius, so that the reaction of converting CO2 to CO occurs efficiently, since carbon monoxide acts as a reducing agent in iron reduction reactions. Direct iron reduction in the blast furnace occurs in several stages. Hematite is first reduced to magnetite, then to viscite, and finally to pure iron. The latter reaction is exothermic, which provides heat for the previous endothermic processes. However, the temperature of from 400 to 800 Celsius remains insufficient to melt the iron, so it remains in a solid state until it enters the hotter zones of the furnace, where the reduction is completed. Direct reduction of iron in a blast furnace occurs through the reaction of iron oxides with carbon in the high temperature range, from 800 to 1600 Celsius. This process goes through several stages, gradually increasing the iron content in the ore. Since all reactions are endothermic, the necessary heat is provided by the exothermic combustion of coke. Reduced impurities such as silicon, manganese, and phosphorus compounds interact with flux and form slag. During the reduction of iron oxides, some of the iron formed is enriched with carbon through interaction with carbon monoxide or directly with carbon at high temperatures. This leads to the formation of iron carbide, known as cementite. The process of saturating iron with carbon at 900 to 1200 Celsius is called carburization, and it lowers the solidification temperature of iron from 1500 Celsius to approximately 1200 Celsius. The efficient use of coke oven gas in the blast furnace contributes to lower energy costs, emissions, and increased economic efficiency of iron production. Injecting coke oven gas into the blast furnace provides an additional source of carbon, reduces the need for metallurgical coke, and improves iron recovery. In addition, this process increases the proportion of hydrogen as a reducing agent, which contributes to lower carbon emissions and meets European environmental requirements. The chemical composition of coke oven gas is shown in Figure 2. Research shows that with increasing coke oven gas injection, pig iron production increases significantly at the maximum level of coke oven gas supply. Blast furnace productivity increases by 26%. This is explained by the complete replacement of natural gas with coke oven gas, which has a strong positive effect on the process. Additionally, coke and coal consumption are reduced by 4% and 15% respectively, which increases the overall efficiency of the blast furnace. Natural gas injection was first used in Ukraine in 1957, and by the 1990s it was used in over 60 blast furnaces. Natural gas injection into a blast furnace reduces coke consumption, CO2 emissions, and improves economic efficiency. Increasing the natural gas supply from 170 to 130 cubic meter per ton of iron reduces consumption by 6 kilograms for 1 ton of pig iron. The chemical composition of coke oven gas is shown in figure 3. However, combustion of natural gas produces water and CO2, which lowers the temperature of the reducing gases and can destabilize the process. There is a technological limitation of natural gas injection at 215 to 230 cubic meters per ton of pig iron. Anthracite is a hard, brittle, and high-energy coal with a low volatile material content that is efficiently used as a coke substitute in a blast furnace production. Its supply through the furnace bell allows to reduce coke consumption without affecting the main process parameters. Studies have shown that when replacing 20 kilograms of anthracite per 1 ton of pig iron, coke consumption decreased by 13.5 kilograms per ton, which is economically beneficial. Coconut is an important element in the blast furnace process, contributing to an increase in the gas permeability of the iron ore charge. Its widespread use began in Europe back in the 90s, where from 10 to 35 millimeter particles were introduced in an amount of from 20 to 100 kilograms per ton of pig iron. Studies show that partial replacement of coke with coconut up to 5% has almost no effect on furnace performance, while significantly reducing coke consumption. Reuse of byproducts in blast furnace production allows to reduce the consumption of coke, iron ore, and fluxes, reducing the cost of iron production. One of the effective solutions is the use of iron and coke briquettes, which also helps to solve the problem of waste disposal. Studies show that the use of 180 kilograms of briquettes per 1 ton of iron reduces coke consumption by 15 kilograms per ton and reduces the need for pellets by 135 kilograms per ton of pig iron without affecting the production volume. Industrial tests when replacing 45 kilograms of briquettes per 1 ton of pig iron confirmed the reduction of coke consumption and a slight increase in furnace productivity, which makes this technology an effective and cost-effective solution. The study suggests a way to improve the operation of blast furnaces by replacing traditional coke with alternative fuels. The use of anthracite and coconut as coke substitutes allows to reduce costs and increase process efficiency. The production of briquettes from metallurgical waste contributes to resource conservation. In addition to solid fuel substitutes, increasing the supply of natural gas and replacing it with cheaper coke oven gas allows for reduced costs and CO2 emissions, which makes these solutions optimal for the environmental friendliness and economic efficiency of blast furnace production. Thank you for your attention.